Welcome once again to our channel. Today we'll be speaking about normalization of data. And to speak on this topic will be a very good friend who has over 2 decades of experience in software development. He's an international consultant who has worked on a number of national and international projects, particularly in the area of IT and software development. Yeah, his work in software development has deepened his use and work around data, and I believe he's quite vast to speak on this topic. Welcome with me, Ambrose Chieke. Ambrose, please take the floor.
Thank you very much, Iti. It's a pleasure for me to be on this discussion with you, where we'll be looking at data normalization and why we want to use it, the strengths, the pros, and the cons, because it's not just a tool that has benefits, it also has its own overhead that you have to be aware of, so you could know if it's the right thing for you to do or not. Okay, so I'll be sharing my slides now so we could have a proper and good discussion. Please, can you enable this sharing? Okay, so I'll be sharing my slides. I believe you can see my slide. Okay. Now, so data normalization, ensuring efficient and consistent database. So what is data normalization? Why would you want to consider using it for your software projects and data warehousing it? So we can't talk about data normalization without mentioning Edgar Hood, because he was the chief proponent for the relational database model, which came into effect in the 1960s. So when you talk about relational database, you're talking about conceiving databases as relational relationships between tables and their attributes. So you model them like that, and they will typically reside in a relational database management system. That's, for example, your MySQL, your SQL server, your Oracle DMS server. All those are examples of relational database systems. So data normalization comes into effect when you are modeling your back end, your database, so to say, into sets of tables and relationships between them and their attributes. Let's say. So if you look at this screen we have here, we have a database table here that talks about lecturers and their courses. So in it will be attributes of the tuple. So each role is a tuple or an entry in the database table. And in this entry, you have attributes, which are the type of data, the fields for the particular attributes. For his, we will look at the lecturer ID, the lecturer name, the hire date, and the course columns. Okay. So when we model our database like this, we are doing it as a relational database table or doing a relational database model. But data normalization helps us to remove inconsistencies, okay, and data redundancies so that we could have finer structures, okay, that are easy and fit into the relational database model as was conceived by code. Okay, so if you look at this data we have now, you will see a couple of redundancies in it. One of it will be you have under the lecturer name column, Professor Daniel appearing multiple times. That adds to the weight of the file, the database file, because even in as much as we're talking about database tables, the weight stored on the system is in files. Okay, so the database itself is broken down and stored physically on the disk as files. So we'll have this redundancy, Professor Daniel appearing multiple times, with the higher date also appearing like that. Okay, so if we enforce or implement data normalization on this, we'll be able to take out a couple of these inconsistencies. We take out a couple of these redundancies so that we have a much more stronger, a much more simpler and data highly normalized data that can actually be useful for our use. Okay, because if I want to update this now, I'll have to update it. The update operation carries a lot of overhead because it will be updating probably just the name, and this name has to be updated across multiple entries. Okay, so that is instead of doing just single updates, we'll be doing updates so that we can make sure the data is consistent in its appearance all over the place. So those are kind of the problems that data normalization will try to solve for us. So, like I mentioned earlier, it has its pros and its cons. The pros is that it eliminates data redundancy and helps to improve data integrity. So you have fidelity of data. Your data is not going to be appearing in different states across multiple locations. In as much so that if you're editing somewhere one centrally, it has to be loaded across all the tables at the same time. It facilitates data updates as data is updated centrally. It ensures data scalability. So with the structure being granular and finely distributed, we could have it scale to accommodate as much data as possible. A database can grow to any length it wants to. It facilitates fewer files per table, like I mentioned, in terms of when you persisting the files in storage, that is physical disk. And one of the cons you have is if you normalize this data, it's going to produce more data tables. So instead of this, if we do normalization on this now, you're going to have two tables coming out of this. And if you further normalize, you could have three tables, four tables. So your data will continue to be finely, the data tables will be increasing. Yes, it helps in terms of conceptualizing your data. But when you begin to want to fetch data out, you have to now start joining multiple tables. That is a big overhead to carry and something you have to consider if you something that will be useful or will impact on the operations of your applications as you develop them. So we see that as cons for normalization. Now, looking at this table, we begin to see the objectives. Why would you want to normalize your data? Like I mentioned earlier, you want to eliminate redundant data. You want to ensure that the dependencies make sense. You want to improve data integrity and consistency. Okay, so your data changes when you only update what portion you need to update without actually having to have multiple operations just because you want to do just one update. Okay, so you see this simple, that earlier table we looked at earlier being decomposed into these two tables. Okay, so you have a lecturer and you have a lecturer consistent. In this case, you see the the opportunity for the opportunity for redundancy is reduced. Okay, so we have your lecturer one way, the courses one way. Okay, so we don't have the lecturers and the courses mixed together, so we could have repetitions and repetitions. This is what normalization can give you. You can further normalize to different lengths as you want. So there are various normalization levels that we have that's in use as of today. We have the first normal form, which we call the 1NF. We have the second normal form, the third normal form, the boys code normal form, which is an upgrade of the third normal form. And we have the fourth normal form and the fifth normal form. Each of them has requirements and what they enforce for you to achieve, for you to be at that normal form level. So for the first one, the first normal form, a table, okay, when I speak table, I use the relational database table, okay, it's in first normal form if it does not contain any composite or multi-valued attribute. One. And secondly, if related data is identified with the primary key. Okay, so the primary key concept it's a key component for the relational database model. It's expected that each tuple should have a primary key, okay, and candidate key and other related data. But the condition to be in the first normal form is that you should eliminate all opportunities for composite or multi-value attributes. If you look at this table to our left, you will see that we have the columns product ID, color, and price. Now, for the color, we have product ID existing in black and in red, and the item number 3 existing in purple and in gray. So your first normal form says you shouldn't have this. Rather, you should break this into two tables where you have the color component on top as a different table and the price component as a different table. So that way you have unary without more simple value attributes existing. Okay, you don't want to have occurrences of multiple. So this has broken down or decomposed this first table to our right into two, and you have this appearing like this. Now you may say one the product ID is duplicated. You're talking about redundancies. Yes, it's IDs, not values, for instance, not text. So the weight of this on Dix is smaller because it's just a number or a reference to a table, not necessarily the content of the attribute. Okay, so this is lighter than having clear text written for for the each of the tuples. Okay, so this is the first normal form. Now, for second normal form, a table is in second normal form if, first of all, it is in first normal form. Then, secondly, every non-primary key attribute is fully dependent on the primary key. Okay, so it might be a little bit, you have to get used to a bit of experience and develop, yeah, to be able to understand fully what this is. A primary key is the key that you can identify as an entry on the table. Okay, so the non-primary key are the other values or that attributes that depend on the primary key, okay, for identification. Now, the requirement says every non-primary key attribute is fully dependent on the primary key. Now, if you look at this our table, we have student ID, course ID, and the course fee. You will see the course ID, yeah, might be directly related to the student ID, but the course fee is not directly linked to the student ID. So we could actually decompose this table into two, such that we have a student ID and a course ID because they are related. While we do another table for the course ID and the course fee because those two will now be related and they'll be dependent on the primary key of those tables. I don't know if that makes sense. So that's what we've done here, following that requirement to decompose that into these two tables. Now, for the third normal form, the requirement is, first of all, the table must be in second normal form, okay? Then the extra requirement says no non-primary key attribute is transitively dependent on the primary key, okay? When we talk of transitive dependency, it implies that if I can deduce A is transitively dependent on B, if I can deduce B from A, okay? Like displaying that on this table by the left, we have that the student ID, the student name, the student state, the student country, and the student age. But if you look, you will notice that the student state, the student country are transitively dependent on each other. For instance, from the country, I can get the state, okay? And from the state, I can get a country, okay? So it makes more sense for me to take out the country attribute and form a different table so that I remove it completely from here and instead have a state. If I need the country, I can always refer it from the country table. Okay, so that's what we have here. And when we decompose this table to our left, we get this table to these two tables to our right. Okay. Now, for the voice code normal form, this is an update, an upgrade of the third normal form. So where we have the requirement that first of all it has to be in a normal form. Then for every non-functional dependency x related to y, x should be the super key of the table. Now, depicting that pictorially, we have this table, the students table, the course table, and the teacher table. Okay, so we have the student table and the course table are related. Okay, because they form the main key of the table. But the teacher table, the teacher column can exist on it because it relates to both of them. Okay, so from a teacher teaches a course for the student. Okay, so we could break that into the student course table and the course teacher table. Okay, and we have that perfectly in the BCNF, that's the voice code normal form level. Now, we also have the higher normal forms, which we refer to as the fourth normal form, the fifth normal form, and in some cases, the sixth normal form. And what is the requirement for it? To be in the fourth normal form, a table must be in the voice code normal form first, and the table should not have any multi-valued dependency. Okay? You shouldn't have any multi-valued dependency. And what does that mean? If we look at the table to our left, we have that they have the students, the major, and the hobby tables. Okay, for instance, you begin to see that the keys there are the students, the major, and the hobby. Okay, but the major and the hobby, okay, can distribute. Okay, there are multi-value dependency on the student, and we don't want that to be in the fourth normal form. So what we do, we need to decompose this table to a student major table and a student hobby table for it to comply to be in the fourth normal form representation. Same way to the fifth normal form is a higher normal form, okay, for normalization, where the requirement is that the table must be in the fourth normal form and it cannot be further lost decomposed, because as you decompose your tables, you begin to lose your data the way it is. So if we can no longer further decompose those tables, then we say it's in the fifth normal form. Now, when would you want to consider? Typically, it's a thing of it's common for us when we implement software development and database designs to always stop at the third normal forms. We stop at the BNCF normal form. That's the boys code, normal form, or the third normal form levels. And because in that case, you're almost approaching good normalization. We don't necessarily have to go further down, because as you continue to go further down, you remember your overhead is you're going to be breaking down into a lot of tables, smaller tables that might be a little bit tricky and complex for you to manage. But if the requirement says your expectation for your software requirements expects you to get as granular as possible, then you could consider doing that. So what are the opportunities for you to consider doing the higher normal forms? If your relationship is going to be complex, you expect to build complex data relationship, okay, then you could, the higher normal forms are candidates for you to do that. Or you want to get better or deeper data integrity and consistency, okay, then you could also consider doing that. Then you are not really concerned about performance considerations, because like I mentioned, as you continue to break down your tables into smaller tables, the performance overhead is when you want to get back your data, probably for reporting or for analytics, you have to consider the overhead cost of joining those tables and to actually form those tables as you need. Okay, so those are opportunities or considerations you could do when you want to adopt the higher normal forms for your data normalization. So, in as much as we have the normalization being a good thing, we also have the principle or software and principle for denormalized data. So, for denormalized data, that is, you are purposely introducing redundancy into your database. And what does that mean? It means I am not bothered about having redundancies where I have repetitions of things appearing. My data can scale. You have long length tables as much as 100 columns or 100 attributes in a table. Okay, those are highly redundant tables, and the benefit is also there, but I don't care because of the purpose of what we use. You will see those kind of tables commonly where you have systems for reporting and analytics. For instance, those of us who do, if you've been opportunity to look at an analytic tools like Tableau and the like, you expect you get better performance when your data is denormalized. Okay, so some databases even exist for that kind of those kind of situations, those kind of implementations. Things like your denormalized data, like your denormalized database. Okay, for that purpose, your JSON databases, for instance, like MongoDB, are chief, or they are based on the principles of denormalized data. So the benefits for denormalized data is your query performance is improved because you're not joining anything. You most likely are just going to query from one table source and do your filtering from that same one table source. So you get the benefits of your queries are simpler and the retrieval for data are faster, which are things you want to see when you're generating reports or doing analytics. So in conclusion, normalization is a key concept in relational database modeling and design. Okay, it helps to eliminate data redundancy, data inconsistencies, and give generalized structure to database tables. Normalization introduces more tables in your table design and hence promotes too much use of joins, okay, which can be complex in query to retrieve data. While some program development scenarios require normalization, higher level of normalization should be considered only when it's absolutely necessary, okay, to use them. So if you don't have any business doing beyond the third normal forms or the voice code normal forms, you just leave it as is, and those ones are already, the data is already fine for you to use as easier normal forms, compliance data. The denomination exists, okay, it exists and it's a practice. Many people are big on it. They prefer that as against the normal data, the normalization data structures, and can also be useful in certain software projects. What I do is needing faster data retrieval, like complex reports and data analytics. Thanks for joining me and listening. You are welcome.
Thank you very much, Ambrose. We really enjoyed those insights about normalization and why to normalize. Thank you very much. Till we meet again. Bye. Bye.